Welcome to Lesson 5D, Reynolds Analogy. We're going to discuss some non-dimensional ratios of these diffusion coefficients that we talked about and something called Reynolds Analogy, and then we'll do a couple example problems today. Here's the energy, momentum, and species 1D diffusion equations, and all three of these guys here are our B's in the diffusion equation. So these are the diffusion coefficients, kappa, nu, and dAj. They all have the same dimensions, as I mentioned before, and if you put them in the same units like meters squared per second, we can make non-dimensional diffusion ratios from them. So these are for the laminar case. We'll talk about turbulence later in this lesson. So we'll define these as three of these here. Schmidt number is defined as nu over dAj. So it's the ratio of momentum diffusion to species diffusion. Momentum on the top, species on the bottom. Lewis number is kappa over dAj, so the heat energy diffusion on top and species diffusion on the bottom. And then finally, Prandtl number, which is the one you're probably already familiar with from your heat transfer class, is nu over kappa, ratio of momentum diffusion to heat energy diffusion. Now, this is kind of silly, but if you want to remember whether these go on top or bottom, when I look at these, I see the kind of the heavier one, the bigger one on the bottom. So nu is just this little tiny thing, and dAj is big, kappa's little, dAj is big, so the heavier one is on the bottom, or the bigger one. This one's a little bit more arbitrary, but kappa, you can argue, has 3 strokes instead of 2 strokes. It's a little bit heavier than nu. Anyway, that's how I remember it. Those denominators are really heavy, dude. So how do you interpret these ratios? Well, let's take a Schmidt number here as an example. If the Schmidt number is small, that means that nu is small compared to dAj. So momentum diffuses much more slowly than species. And if it's large, it's the opposite effect. And then you can argue the same thing with Lewis and Prandtl number. So then I want to talk about Reynolds analogy for these laminar cases. And it turns out that energy, momentum, and mass all diffuse in a similar fashion due to molecular diffusion. So let's think about how this works. Let's take, for example, temperature, and suppose we have energy diffusing upward. So this is the case where at time t equals 0, we suddenly have a flat plate here that becomes hot. So the temperature is T naught everywhere, this some ambient temperature. At t equals 0, the whole room is at T naught. At time t equals 0, suddenly this is at Ti, some initial temperature. And then what happens is energy diffuses, so there's an energy flux, and it's felt by the temperature increasing in this fashion, and it just keeps spreading out. So eventually this would get the whole room, if we're assuming this is an infinite space though, but everything would get hotter. So the rate of diffusion depends on kappa, this thermal diffusivity, which is the diffusion coefficient for energy or heat. We can make an analogy here. So here's what Reynolds did. Reynolds is the same guy that we honor with the Reynolds number that you're familiar with in fluid mechanics. He argued that momentum is diffused upward in the same way, except it has a different diffusion coefficient, nu, which is the kinematic viscosity. So you can visualize this as a flat plate that everything's 0 velocity in the room, and then suddenly this plate starts moving. This is some infinite plate, starts moving at velocity u, speed u to the right. And so you get this kind of boundary layer building up, and as time increases, the momentum flux is vertical. But I literally copied and pasted this figure into this figure and changed the labels because it's exactly the same process, and mathematically we have the same equations. These are all the 1D diffusion equations, just with different properties. So energy and momentum have exactly the same equation. They just have different properties that are diffusing and a different diffusion coefficient. So these look identical, and they have the same equations, actually the same curves. And then finally, the mass one, or species, is diffused. This one's a little harder to visualize or imagine, but let's suppose we have a liquid that is sitting here with air on top, and there's no vapors in this air, and maybe there's like a thin sheet of plastic on top of that liquid, and then suddenly at time t equals 0, the plastic sheet magically disappears, or we quickly remove it without disturbing anything, or if, say, it's a little ice sheet and it suddenly melts or something like that. So suddenly this liquid is exposed to the air, and so it has some molar concentration right at the liquid surface, which is always related to the vapor pressure of the liquid, by the way, vapor pressure of that substance. So the PJ right there at the surface is PVJ for that particular chemical. And so mass or species diffuses as time increases. And again, I copied and pasted from the previous figures and just changed the labels. So we go from C mole or I, the initial, to, in this case, 0. And the only difference here is T doesn't go to absolute 0, but it's some T naught, whereas these go to 0 typically. U naught is typically 0, and C molar is typically 0 far, far away. So that's the Reynolds analogy, and this is all for laminar flow. And so this Reynolds analogy is very useful because we can do experiments and stuff with heat transfer, which is the easiest thing to measure because you could just put thermocouples everywhere. And we can apply them to momentum and we can apply them to mass. And so that's why sometimes, and we won't get into much of this here, but when you look into the literature with species diffusion and how species are diffused in liquid containers of liquid or puddles of liquid, you'll see things like Prandtl numbers in there. And like, what the heck is a Prandtl number doing? And Nusselt numbers. These are all heat transfer kind of things, but they work also with species diffusion because of the Reynolds analogy. Now let's look at the Reynolds analogy for the turbulent case. So again, energy, mass, momentum all diffuse in a similar fashion, but now it's due to these large turbulent eddies which promote rapid mixing rather than the diffusion coefficients. So just as a quick review, laminar diffusion or molecular diffusion is very slow, whereas turbulent diffusion with these large eddies is much faster. I talked about this in a previous lesson, but if we have air molecules that are bouncing around due to Brownian motion in the laminar case, and then we have some particles in here that they'll also bounce around, and so you just get this slow diffusion due to Brownian motion. But in a turbulent case, if you have some particle here, it could be swept up to this part and this one can be swept down to this part, and so the diffusion is much, much faster. We can say then that the turbulent kinematic viscosity, if you want to call it that, turbulent kinematic viscosity, nu sub T, is much greater than nu, the laminar one. Similarly, thermal diffusivity, kappa T, is much greater than kappa laminar, and then turbulent dAj, much, much greater than dAj. So what the Reynolds analogy says is that we can easily measure heat transfer characteristics, but since it's harder to measure mass transfer, we can use these heat transfer correlations, Nusselt number, Reynolds numbers, etc., to predict mass transfer behavior. And they're analogous by Reynolds analogy. So we can define these turbulent ratios, non-dimensional diffusion ratios, turbulent Schmidt number, SCT, nu T over dAjT. So these are exactly analogous to the laminar ones, except we put a subscript T everywhere. Lewis number, kappa T over dAjT, and Prandtl number, nu T over kappa T. And here's the key, and Reynolds was smart enough to figure this out, and that is, since the species here is diffusing very rapidly due to these big eddies, then also heat, if this was a hotter piece of air, a little parcel of air that's hot, it also gets transported in exactly the same way. Or if it's momentum, you have some kind of a boundary layer going on, that faster air gets transported up here by this same eddy. So what Reynolds said was that all these things, heat, momentum, and species, should diffuse in the same way. In other words, we expect that all of these non-dimensional turbulent ratios are approximately 1. So in other words, nu T is the same as kappa T is approximately the same as dAj turbulent. And so any of these ratios would be 1. In other words, all properties diffuse at the same rate. So I summarize, for turbulent flow, all diffused properties diffuse at approximately the same rate. This is the beauty of the Reynolds analogy for turbulent diffusion. We're talking about turbulent flow here. So now I'm going to do 2 examples, one for laminar flow and one for turbulent flow. And for the laminar case, this is just a qualitative question. We have a laminar boundary layer on a flat plate with a velocity boundary layer and a thermal boundary layer as sketched. So this is the velocity boundary layer, U. U goes from 0 up to U infinity. And then this plate is hot, so T goes from some high temperature to some temperature that's not necessarily 0 there, but some room temperature. And then there's a thermal boundary layer thickness, delta T, and a momentum boundary layer thickness, or a velocity boundary layer thickness, delta U. So here's U infinity, and there's some T infinity out here, which is what this goes to, T infinity. So the question is, which Prandtl number is this, less than 1, equal to 1 roughly, or greater than 1? I labeled the thermal boundary layer thickness and the momentum or velocity boundary layer thickness, as well as the boundary layers themselves. And so here we can see that delta sub U, which is the velocity boundary layer thickness is greater than delta sub T, the thermal boundary layer thickness. So that means that momentum diffusion is greater than energy diffusion, which then means that nu is greater than kappa. And remember, the heavier kappa is on the bottom, so Prandtl number is nu over kappa, and if nu is greater than kappa, then Prandtl number is greater than 1. So this C was the correct answer. Now, for example, water has a Prandtl number of about 7, so this would be similar to what you might find in water, whereas air has a Prandtl number of about 0.7. So air would have the opposite effect. The thermal boundary layer would be a little bit thicker than the momentum boundary layer, but for water, it would look more like what I sketched there. Okay, let's do one example for turbulent flow, turbulent Reynolds analogy. So this is based on some research that I actually did a few years ago with 3D printers. They give off some nasty vapors, some of which are harmful, and also some particles, but we were looking at both vapors and particles from the melted plastic. The actual configuration on the left here is a 3D printer, and there's some kind of event where vapors are being discharged, and there's 3 locations where we'll talk about the concentration of that vapor. And so let's look at this situation where Hannah does not have a detector for this vapor. So to stimulate it, she puts a heater in a box. So this simulated configuration here is a heater, same dimensions, same exhaust. So we have the same flow rate, just a heater that has warm air coming out. So there's diffusion of energy in this situation and diffusion of species in this situation. But she makes everything identical. It's the same shape, same speed. It's in the same room. And we're assuming that the room is turbulent. So whatever vortices and eddies are in the actual case or also in the simulated case, it's the same room. So we can measure easily. She just gets a thermometer or a thermocouple and measures the temperature at 3 locations, A, B, and C, and I give those temperatures here. And C is considered far enough away that it's room temperature. So this C is the same as it is out here. Out here, it's far enough away that it's basically at the room ambient temperature. And so the same thing would apply in the actual configuration, except we're talking about the concentration of these vapors. She doesn't have a sensor to measure that, but the manufacturer, she looked through the specs and found that it's 35 milligram per meter cubed at this location where the vapors are coming out of the printer. And we'll also assume that C is at infinity for that case, since this is Reynolds analogy. So to predict the mass concentration of the vapor at location B, where the operator is breathing, that's what we wanted to know in the actual configuration. So how do we solve this? Well, it's actually a very simple solution. We're assuming it's turbulent. So the Reynolds analogy holds. So we know that diffusion of species is the same. It's analogous to diffusion of heat in the form of temperature measurement. So we can set up a simple ratio. And so I'll simply say that the mass concentration at location A minus the mass concentration at location B divided by mass concentration A minus mass concentration C equal the same thing in the simulated configuration, except in terms of temperature. So all we have to do is solve for CB and plug in the numbers. And I'm not going to write everything out. This is a very simple problem. And it turns out that C is 0, roughly 0. We're neglecting it at infinity. And so when you plug in the numbers, and you can work on this on your own if you want to make sure you get the right number, you get CB turns out to be 3.97 milligram per meter cubed. And we can be fairly confident of that based on our heat transfer experiments, provided that these are geometrically similar situations and that the room currents and everything are the same. This will be a very good approximation since all those diffusion coefficients are pretty much the same for the turbulent case. So that is the beauty of the Reynolds analogy. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.